Recording in progress. Okay. Optimization is something general. It applies to any research field also, from material science, engineering, business, economy, species reproduction, biology, biochemistry, psychology, crazy people, etc. Anything. So this is an example. Area and perimeter. Let's. Why this doesn't work? Let me see. Should work. Let's now. Okay, here. No. Like this. But it always go where I don't want. You have this fence. This one, the figure. Look, this figure, and then you want to maximize the area. Maximizing the area. This is a basic exercise, and it seems to be silly, but for example, sometimes you want to maximize the revenue of a company, or sometimes you want to maximize the performance of an organization with some metrics, or sometimes you want to maximize anything. You will to analyze. Then this example is precious. A homeowner has $320 to spend on building a fence around a rectangular garden. This amount is fixed. He only has $320. Three sides of the fence will be constructed with a wire fencing, which costs $2 per linear foot. So for each foot is $2 one, and the fourth side will be constructed with a wood fencing, which costs $6 per foot. Find the dimensions and the area of the largest garden that can be enclosed with the $320 worth of fencing. The largest area. So this is an optimization problem. It's one of the most basics. It's like finding the largest window in a room, or finding the largest volume with the fixed material. For example, one problem could be, with a fixed material, try to make the largest possible volume. Let's assume you have this classroom right now here. Maybe the guys who designed this classroom, they did some optimization problem, because they try to find the maximum volume for a fixed amount of material, such that there is a lot of space. Or maybe they didn't care the volume, they cared the superficial area, anything. But it's something to consider. So let's go to the example. Fixed is 320. And $320 is fixed. The area, how do you find the area of this rectangle? Area of a rectangle. Let's write here. Area, oh, is it one? Area is this one, right? You have the fence here. You have Y, X, X. The area is naturally XY, right? So you have one equation with two variables. This is what you want to maximize. How do you maximize? Calculus, maximum and minimum. But you have to convert this problem, you have to use the constraint of the money. How do you use the constraint of the money? $320 is the money you have. So that will constrain this quantity, the perimeter. Because the longer you construct, the more you spend. Then look at this equation here. This is the cost of the fencing. $2 multiplied by the length, which is Y, plus $2 multiplied by Y again here, plus $2 multiplied by X, plus $6 multiplied by X. This is the perimeter cost. And this is fixed to be 320. Then you have this equation. 320 is equal to 2Y plus 2X plus 2Y plus 6X. So at the end is 4y plus 8x, right? Look at this. You have to maximize this area subject to this condition, which is what we wrote here. Then what do? You have two equations with two variables. You have to kill one of the variables. How do you kill one variable? With a gun. You have to eliminate one variable. So you can solve, for example, you can solve y here. Y is 80 minus 2x, right? 320 divided 4 is 80, right? And a divided 4 is 2. And you solve for y. These equations are equivalent. Then I can replace this in this equation. And then I have that the area is x multiplied by y, but y is 80 minus 2x. Then this gives me 80x, 2x squared. And then I apply the criteria of derivative here. Derivative of a with respect to x equals 0. Okay, let's find the derivative. Derivative 80 minus 4x equals 0. So what's the solution? 20. X 20, right? If x 20, when I replace here, I obtain some value for y. It will be 40. Y will be 40. Let's see if we did it correctly. This is what you just did just now. This is what we did just now, this. Okay? Then everything else is maximum and minimum. And how do you know what is a maximum? That this is a maximum. Second derivative of this is positive or negative. Let me delete this part here. Let's calculate the derivative again here, because it's not clear here. Derivative of this function here. What we did is to solve, we did this, right? We solved for y, we found this equation. We replace this equation, this y here, in this one. And then what do you get? This equation in area. Now find the derivative of this. Derivative of a with respect to x is what? 80 minus 4x. Hmm. 80 minus 4x equals 0. This is 20, right? 20 in the units, in any units. I don't know if it's meters. I think it's feet. They do it per feet, no? Because the price is per feet. So then you replace this inside the definition of area. Inside this definition, 80 multiply 20 plus 2, sorry, minus, let me delete here, 1 second. For being clear, well, let's do it here, in this part. This part. Okay, I want to do this. Okay, here, this is 80. I want to replace the 20 here. A of 20 is 80 multiply 20 minus 2 multiply 20. This is equal to what? 1,600 minus, and this is a square actually. 800, right? So I give you 800 feet square. This is the largest area you can do with that fixed price you have. With $320, you can make 800 feet square, the largest possible area you can construct. So this is an example of optimization problem. Now I will show you another one, more realistic. Maximizing revenue, those guys who are in business. Revenue and profits. Something familiar for you. An office supply company sells X permanent markers per year at P dollars per marker. The price demand equation for these markers is this. P is the price, X is the demand. What does it mean when the demand increase? What happened? Well, it doesn't matter. Later you will realize. What price should the company charge for the markers to maximize the revenue? What is the maximum revenue? Then revenue is price multiply demand. This is the price. You multiply by the demand and you obtain this equation, which is quadratic. Now, how do you maximize this revenue? You have to apply the derivative. Derivative of the revenue is 10 minus 0.002 because this 2 multiplies this 1 and becomes x. This is the derivative of this function. And if you send this equal to 0, you obtain the value of x for which the revenue is a critical revenue, either maximum or minimum. What is the second derivative of this? It will be negative. It's clear that the second derivative is negative. Derivative of 10 is 0. Derivative of this is minus 0.002. So it means that the critical point will be a maximum. The solution of this equation will give you the maximum revenue, maximum possible revenue. And the maximum revenue occurs when the demand is 5,000. When the X is 5,000, you replace 5,000 here. 10 times 5,000 is 50,000 minus the times 5,000 squared. Whatever you get is the maximum revenue. Is clear this example or is not so clear? Or you need to do it step by step on the board? Of course. Not a big problem. Not a big deal. Let's put like this. The price, usually in these theories, you have the price as a function of the demand. In the airlines, for example, when you analyze airlines, what's the relation between price and demand? Qualitatively speaking, when the price increases, the demand decreases. When the price decreases, the demand increases because people want cheap tickets, no? So there is a relation between price and demand. These guys arbitrarily give me a relation between price and demand. They tell me the price is 10 minus 0.001x. X is the demand. Demand. P is the price. Revenue is price multiplied demand. We know this. You multiply the price by the demand, that gives you the revenue. Revenue minus cost gives you profits. You should know that from I don't know, those guys who are in business. So price multiply demand is 10 minus 0.001x multiply x. And this gives you 10x minus 0.001x squared. I want to maximize the revenue. I find the critical points, the R, the X equals 0 is equal to 10 minus 0.002x. And now I solve for x. X is equal to 10 divided 0.002, which is 5,000. 5,000 what? 5,000 persons, 5,000 units, whatever it is. But that measures the demand. Usually it's the amount of sellers, no? Then with this 5,000, you replace this number in the revenue here, and that gives you the maximum revenue. Because the second derivative, if I evaluate the second derivative of this, second derivative is equal to minus 0.002. It's smaller than 0. This means that at 5,000, demand the revenue is a maximum because the second derivative is negative. Then I will replace 5,000 in the revenue. It gives me 10 multiply 5,000, which is 50,000 minus 0.001, 50 squared. And whatever the number gives you here, that's the revenue. 50,000 minus, this should be what? 2,500 maybe? And this is 50,000 minus something very small. Well, because you have to multiply for 10 to the minus 1, 2, 3. So 1, 2, 3, 2.5, yeah. It's 2.5. So this is also actually quite small. So actually this is the maximum revenue. The maximum revenue you can get from in this problem. Then you can see that optimization is quite useful. Now, in the real life problems, you have more than 2 variables. You have many variables. So the optimization problems are more challenging. But still you can play as what we did in dimensional analysis. You fix constant some variables and find the relation between 2 variables. And then you fix other set of variables and find the connection between, and so on, and so on, and so on. And then you can analyze individually what is the behavior of each variable, what are the possible optimization problems emerging, etc. Optimization is a powerful weapon which you can apply anywhere in any research field. In more complex problems, you can simultaneously include many variables, maybe with some algorithm or program or software, you can find the ideal conditions for a system to operate, and that's called optimization. So any questions so far here? Now you can see how powerful is calculus, how useful it is once you know the connection between variables in a problem. Questions, comments, etc. Yeah. Right. Here. It's an epidemic. It's fire everywhere. No, it's okay. You go. No, I mean, you don't have to tell me anything. Just go. My goodness.